I'm Harley.
Alright, so when I poured water into this cylinder, stop talking. Especially you all, because it is very close. Here, that frequency that you're hearing and this frequency are very close. Maybe they are exactly the same. So this is 384 hertz. Okay, so 384 hertz, it is resonating right now. So where is the antinode? At the top. Where is the node? At the place where the water is, the water is basically the closed end.
Equalizer. You think holding it by the string, you could get the fork to touch the water without breaking the glass? A little bit of operation.
It's risky.
No, you got
it. I'm just gonna hide behind.
I could take it down like that, but not.
Do it. Oh God, I can't watch
Okay.
Just imagine it shattering.
All right. So, in 34 years, I've not broken anything. So therefore, don't break anything. So therefore, resonance is clear. So as I said, antinode is up here and node is up here. So therefore, now when you measure the distance from there to there, you are able to get the length of the tube. So this is pretty much what is happening. That's a closed tube, and this is an antinode, and that's a node. So the pressure is high here and low here, and that is what we symbolize by this thing. So the antinode and the node and the length of the tube that you actually, not the length of the tube, length of the air column. If I measure the length of the air column, that should be equal to lambda over 4. And that should be able to get you the lambda, which is 4L. Now there are some technical issues over here. The antinode is not formed at the edge of the glass. It is formed a little distance away from the edge, like there. The antinode is formed at this level, not at that level. And that is what is known as end correction. End correction. And the end correction is 0.3 times the diameter. The end correction is 0.3 times the diameter of the tube. So the wider the tube, the end correction gets bigger also. Like for church organ pipes, because the organ pipes are so big, the antinode is going to be like far away. So the antinode is not at the rim of the tube. Antinode is away from the rim. And how much is it? It is 0.3 times the diameter. I can measure the diameter and tell you how much it is, and we're going to do the calculation for the speed of sound here. So the diameter comes out 4.6. 4.6 is the diameter. So tell me the end correction.
1.38.
1.38 centimeters is the end correction. Now I'll tell you what exactly is the resonance length. So the resonance length is 20.7. 20.7. So now add 20.7 to 1.38, and then it divided by 10. Oh, so 100 to change it to meters, and then multiplied by 4. Tell me the wavelength.
0.8832.
0.8832. That is in meters. Now the frequency of the fundamental is V over 4L, or V over lambda. So that's your lambda, V over lambda. And frequency is the same as the frequency of this tuning fork because it was in resonance, right? Mm-hmm. Because it is in resonance, it's 384. So frequency is known as 384. So 384 is equal to V, the speed of sound, over lambda, which is 0.8832. So what is the speed of sound? Go ahead.
339.15.
339.15. Yeah. That's the speed of sound right now.
What's the actual speed of sound?
That's it.
We just found water.
Well, I didn't know like if you were like a little bit off because like you're.
Yeah, I'll tell you why it can be off slightly is speed of sound changes with temperature. For every degree rise in temperature for a delta T of 1 degree Celsius, the delta V, the speed of sound changes by 0.6 meters per second. For every degree rise in temperature or fall in temperature.
That's crazy.
It is a big change.
Is that because like water,
No,
like
speed
in
of,
the air, or is it just?
speed of sound depends on the temperature because when the temperature is higher, the particles are more agitated already. So passing on becomes easier. Passing on the energy becomes faster. That's basically what it is. It's like me trying to ask someone here to pass a certain book to the far end in the first period versus asking the same thing in the last period. Last period you're going to be overexcited. First period you're kind of sleepy. Here's a book. And then here's a book. You know, your speed is affected by your temperature. If your temperature is higher, you'll be starting to act faster. You get it? Yeah. Yes. Yeah.
So we measure both. I know in physics you measure a lot of the speeds of stuff like light, sound, and other various things at generally 0 degrees Celsius, correct?
No, we can find out at 0 degrees Celsius. We're going to do that right now.
But if I looked up speed of sound, it would tell me what it is at 0 degrees Celsius, probably, right?
Yeah.
Yeah. So what is it at? So at 0 degrees Celsius, the speed of sound is like
330.
All right.
Roughly 330-ish. So how are you going to find it out? So this is speed at this temperature, and the temperature right now is approximately 24 degrees Celsius. So this is the speed at 24 degrees Celsius. So what is the speed at 0 degrees Celsius? For every degree, this is the change. Yes, Hunter? Can you get this?
Yes.
Good. Tell me the answer. I want the answer. This is the speed at 24 degrees Celsius. And for every degree, it is a difference of 0.6 meters per second. So when you're coming down 24 degrees, you're going to come down 24 times 0.6 below.
24.75.
How much?
324.8.
324.8?
Yes.
That seems kind of wrong, right?
Yeah.
Because 330 is approximately the answer. Can you tell me why?
Our measurements aren't like
error.
perfectly accurate.
Error.
What error?
Well, like in measurement, because you're like your measurements aren't specific enough.
Anyone to find out where the culprit is? Why I'm not getting close to 330 and why I'm getting
Because that measures in Fahrenheit, so you.
no, I changed it
estimated.
already. I changed it, but again, where is the reason? Yeah.
The changing velocity not exactly 0.6
Yeah, it is not exactly. It's like 0.59 something. Yeah, that is one of the factors. Another one,
Google
a very important one.
The temperature generally around that table could be colder or warmer than what the thermometer.
You're close to the right answer, but can you make it more
The
specific?
frequency would be different because the water would be ice.
No,
The temperature inside of the tube is not the same as the temperature around the like where they're measuring at.
that is right because the temperature of the water, I collected the water from the tap, is much colder than the temperature of the room. So the temperature of the water should be the one that I should have looked into, not this room temperature. You understand? If I looked at the room temperature, I'm wrong. The temperature of the water is probably just 18 or something like that. So you have to take that into account. The temperature of the actual water should be taken into account.
So the temperature of the water.
This is actually much lower than 18.
So the measurement of the temperature of the water at the time we measured was roughly 15.5.
Then you should be
degrees
taking
Celsius.
that as this number is actually at that temperature, so
Yeah,
you
it's
bring
got-
it down by 15. So 15 times 0.6 is out.
It's
9?
9.9.
Take 9 out.
Yeah.
That is 330. You get it? Make sense? So errors can happen like that. Now, this also kind of prompts me to remind you about, for example, an AP test. Most of the questions are more lab-based, sort of. So sometimes they'll tell you a student wishes to measure the speed of sound in the lab using a resonance column or using a resonance technique. And here is a list of gadget materials that he can pick to do the experiment. So if it was you, what instruments will you, what stuff will you pick? And in the big list, they will tell you beaker, water, meter stick, tuning fork, a thermometer, a scale, a weight, whatever. They'll give you a list of items, and then they'll expect you to kind of figure out how. So first thing is they'll ask you, check which things will you use. Now, you can check the ones which you are actually going to use, that's fine. And the next thing is describe how you will use the stuff that you have checked in order to find the speed of sound. So literally you're going to do write up exactly what I've just shown. You understand how it was done? Strike the tuning fork, change the level of the water, and get it? And that's exactly what you write. Now, is it wrong to check the thermometer as one of the options? It's not wrong. It's not wrong to check the thermometer in the list as long as you explain what you use the thermometer for. Make sense? If you check thermometer there in the list and you mention nothing about the thermometer in your write-up, then that is loss of point.
How many points do you think you would get if like
How many
you don't need water, but like you put water and you said like I'm using the water if I get thirsty?
I mean, you can't do experiments while you're dehydrated.
Well, you experiment with the invigilator, with the one who is checking your papers, with the reader. That is
I'm a writer.
exactly. Yeah, when I have done this grading also, I've seen some students write, prayers, prayers at the end. For some reason I'm totally lost. Please, this and that, and then I pray for your family and blah 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 that stuff. So yeah, you look at it and you're like, he's ready to pray for my family if I give him some more grades about it. Okay.
What if he busts out the Ouija board though?
Again.
He wrote down the Ouija.
So did you get this point clear? So you have to describe. You have to describe the experiment in such a way that all the materials that you've chosen is appropriately used. If you've chosen something, then you should use it properly. So thermometer, if you have chosen the thermometer, then you can say, I'll check the temperature of the water to find out what's the temperature of the air right above the water in order to find out the temperature at the water's temperature. So this speed that he's finding out is not at room temperature but at the water's temperature. Make sense? So that is, yeah, go ahead.
So are we going to do like any kind of practice with open answers for the AP physics test on that note?
We will. As soon as we are done with this and electricity, we are going to start off. And so standing waves in a tube. Now, you can have standing waves in this tube too. Okay, and I will show you that in a moment. I'll do it here. So I'm using the frequency generator.
No, he didn't.
And I'm using this speaker that came from a television.
Did you scrape off the barcode of the television too?
Now,
Speakers.
oh, I can check that also. I can do that also. So you don't have to have a tuning fork to do it. You can actually do it with this. So I'm setting up the sound and I'm keeping that right there. And do you hear any resonance?
Yeah.
No difference. But when I bring it to that 384 mark, That one.
This hurts.
Well, like you know, like a speaker, like does the speaker constantly change to match the resonance of like
Hold on,
some
hold on,
smaller
hold
speaker and then it makes a really loud noise?
384.
And it just vibrates at the speed of the wave.
You can make like a really fancy speaker, like a bottle of water next to the speaker. It's stupid loud.
You can hear the difference. Okay, that's the resonance.
Yeah.
That is close to 400. That is 384. Should be 384. The same way here on an open tube. This is an open tube.
So if you just held the tuning fork up right now, would it be going nuts?
It should be. Yeah, see, that is an open tube, and I'm just keeping this here, and I'm changing.
Yeah.
You hear the resonance?
Yeah, that's crazy. So does the speaker just work to match the resonance of the
Yeah.
music or whatever you're playing?
The frequency I'm setting here to match this one, and once I skip that,
So I was right. And then
see, it's out of resonance now. It's out of resonance now. Now it's not able to set up this. Now it will set it up once again for the second. Second harmonic. First overtone. The first overtone.
Bruce was right. Coach works with a lot of electronics. I feel like you should take that thing into an airport and have it hit.
Yeah. You see it? You can see the increase in amplitude. Well, a tuning fork will be the best one because it is like pinpointed. Now speakers are more, especially this speaker. This speaker is like spread out, so therefore it's kind of, it's not a pointed source. What do you say?
I think you hold up the tuning fork to see like what it's vibrating. You hear the frequency.
On this,
Yeah.
I can't change the length of this because the tuning fork.
No, we're talking about on the.
Like the speaker.
You put it at like
On
284.
this?
Yeah, you put the.
If you put the speaker up to the tuning fork,
Watch it.
Oh, you mean like strike it and put it like that?
No, like put on the speaker.
Oh.
The same.
Oh, same frequency.
Can we keep the tuning fork like somewhere on the other side of the room that we can like, distinctly hear from two nodes?
This matches. I'm going to talk about that right now. So you understand the resonances and overtones in strings and air columns? Okay. Now, next one, interference of sound. Interference of sound. You know interference of waves altogether, right?
Yeah.
What are the different kinds of interference that you've seen? Constructive and destructive. So you can have constructive interference and destructive interference when two waves or more pass through a medium. When two or more waves pass through a medium, it's going to create constructive and destructive interference because there are two waves. And again, I'm showing you waves like that, but in sound, waves are in the form of compressions and expansions. Since we cannot draw these compressions and expansions that well, it's better to draw it. So if one frequency is this, and if the other frequency is this, the frequencies are different, right? When two of them are sounded at the same time, watch what's happening. At this point it is constructive. Can you see that?
Yeah.
At this point it is destructive because one is up, one is down, so it's destructive. And at this point it is constructive again and destructive. constructive, and constructive. So what is going to happen is when two sounds are sent out into the same room and the frequencies are slightly off, what will happen is it will send it'll send this entire thing to your ears. So what will happen is at some times you're getting a constructive tone, which is basically loud. At some other times you're getting a destructive tone. So if one's frequency is F1, if this one is F1 and if this one is F2, you're going to hear beats. It's called beats. And how much is a beat frequency? Beat frequency means not F1 nor F2. It is at what rate are these constructives coming to your ears? At what rate are the constructives coming to your ears? That's called beat frequency, and that is the difference of F1 and F2. It's a difference between F1 and F2. For example, if F1 is 256 hertz, if F1 is 256 hertz, and if F2 is 260 hertz, you're going to hear a frequency of 4 hertz. Now, what is that 4 hertz? You're going to hear waxing and waning. It's called waxing and waning. Waxing means like louder sound. Waning means lower intensity. So waxing and waning is what you hear, ups and downs. You will be hearing ups and downs at what rate? 4 per second. So you're getting 4 per second. So like 1, 2, 3, 4 of them per second. That's called waxing and waning, and this is called beats, beat frequency. Before I show you that, let me also show, tell you something that you will remember. At a stoplight, you have noticed these things and probably just took off your head. At a stoplight, you're waiting to take a left signal, left, and you're stopping, and people in front of you are also having the indicators on, and you're looking at 2 cars having the indicators on, and at sometimes you'll see they're both together,
Yeah.
and then after some time they go off,
Yeah.
and after some time they come back again on,
Right.
and then again after some time goes off. It's because they both have different frequencies. So how many times do they match up per second? That is called beat frequency. You get it?
So
The same with the swing. If one swing is slightly shorter than the other swing, one's frequency is a little more than the other. So if you swing both of them, they go like this. Initially they go like this, but one of them goes faster. And then there will be delay of the other one. And then finally you'll find they're going completely opposite. And after some time again, they'll come together and then. Notice it?
Yeah.
That is the concept of beats. That is the same idea of beats. And beats is used by musicians to tune their instruments. To tune instruments, they can use beats. Yeah.
So it's never negative, right?
No, that's why I said the difference.
Okay.
A symbol that you see here is implying difference, not a minus sign.
Oh.
This is not a minus sign, it's a different sign. So if you see something like that in math, it's only saying the difference.
You just do the absolute value.
A kind of absolute value. Yeah. If this sign is used instead of a minus sign, that means you algebraically don't subtract, instead find the difference. That's a symbol. Okay, so that's beat frequency, and I'll show you the beat frequency.
Hello, YouTube. How are you today?
This is broken. Somebody broke it.
No, I'll kill him, Johnny.
That was
Somebody broke it.
It was a character.
Obviously,
Ah.
it's a sacred object.
Well, we can break them.
Are they still good?
Now, see this?
That's an immediate threat.
This mechanism that you see here is to change the frequency. Now, this one's frequency is different. See this? That frequency is different from this frequency. This is lower, right? But if I hit both of them, hear the beats?
Yeah.
Ups and downs? It shakes. Now understand one more thing, that when you're hearing ups and downs, everybody is hearing at different times. Yeah, when it's up for you, it may be down for him. But it's all coming together so fast, that's why you don't actually differentiate. Right? The way you're hearing it, ups and downs. Now, can I make it smaller? I make the difference less. Now it's... Now, I don't know how you hear it, but can you put your hand up to say when you're hearing high and low? And I want to see if you're matching up. It's all different. It's all different. It's all different. I'm going to make it still slower.
Yeah, make it as slow as you can.
So, yeah. Can you see the difference? Because the wavelength of this sound is roughly like a meter.
Hey Jacob.
And that's why there is a difference from one position to another position. It is going to be different. If it is waxing at this point, it's going to be waning here.
So can you make it
So-
like dummy slow?
Make it huge.
Make it super fast.
I didn't even
That's
hear
too
it.
slow.
Yes, too. Can you see it's going up and down?
Dude, make it really fast. Right on the top.
Super hot.
Now, some of those things will be really like...
Make it super high. Higher.
What's the worst thing that happens if
It's really fast.
That's cool.
Wait, really?
It's too fast.
You can't really hear
Are
it.
they just so far
No,
apart that
you
it
can
doesn't even matter?
We're so close together.
It's very close together. So, this frequency is far away. Therefore, you have a higher
Oh,
mix.
yeah.
Now, about this thing, about this tube, when you blow air, it is going to set up, this is a tube, right? So it is going to set up your fundamentals and overtones and stuff like that. Now, the smallest disturbance that can be sent here is the fundamental. And that's what, when I swing it like that, what you're hearing right now is the fundamental.
Can we video this?
And when I do it faster, you will hear the first overtone. That's the first overtone. You want second overtone? It's not doing it well.
Can I swing it,
As
Coach?
fast as you can go.
Can I swing the sacred tube?
You see, I have to get a different one.
Can I take a shot at it, Mr. Sam?
You can. Yeah, that's fundamental. It's not doing well.
Go. Here we go, Jacob. Let the music throw around the sacred
Wait,
tube.
Mr. Sam, this is something that you broke.
No, get the fundamental first.
Fundamental.
No, that's not
That's the
good.
second.
Oh.
Will, sit down.
Yeah, that one. That's the fundamental.
So fundamental,
Yeah,
guys.
second.
Then a few steps
And-
up from the fundamentals, this bad boy. Sorry, John.
You guys are
Here you go,
going.
yes.
Jacob, go as fast as you can.
There you go.
That's fundamental. First overtone, second overtone. Next one. Next one.
You gotta keep it serving for the second minute.
That's everybody.
That was hard.
Wonder if there's a way we can attach one end of that to a drill.
Okay, now I'll show you what is interference of sound. Watch this.
It's not making a sound.
Burst over.
That's not perfect.
I'm going to show interference of sound
No, we're going to
Now, okay, pay attention here. Pay attention here. Pay attention here. Now, I've connected the two speakers together. I've connected the two speakers together. So if I'm playing the sound, watch it. Both of them are sounding the same frequency and together. You hear it?
Yeah.
They're both together, right?
Yeah. I got you, coach.
This is here. This is a different sound. This is same sounds,
Yeah.
but they are constructive, and so you hear it. Now what I'm going to do is, I'm going to flip the wires.
Coach, you sure about this?
I'm going to flip the wires. So that one is working normal. I'm going to flip the wires. Oh, this way. I'm going to flip the wires and connect the speakers now opposite.
It's the opposite of ETO.
Now I connected opposite. Already you can see the difference,
Yeah.
right? So what's happening here?
You're sending out counteractive waves.
So one is doing compression, expansion, compression, expansion. The other one is doing expansion, compression, expansion, compression. So if I put these like this, you hear both of them?
Yeah. Yes.
And I put them like this,
Oh.
it kills each other. Destructive interference. That is destructive interference.
That's wild.
It's coming together now. Position differs.
It does. I can kind of
That sounds like the ETL. That sounds like the ETL.
I'm glad we're all deciding. You know what? Wait, so Mr. Seal,
Yeah.
was that how a jam works?
No, that's not how a jam
That's-
works.
I will
Oh, you got it.
I honestly thought that was bad.
I honestly thought it was just good off because my ears were still ringing.
Yeah, I know, yeah. It sounds pretty good.
I will kill you.
Again, seriously.
I will kill you. Damn.
It sounds pretty close.
Yeah, sure. It would be a shame if